In an oil drop experiment, a negatively charged oil drop, and that's right over here, has a mass of 4.5 times 10 to the minus 15 kilograms and is held at rest between two parallel plates separated by a distance of 4 centimeters. Parallel plates, there's a separation. The potential difference between the plates is 920 volts. Draw a free body diagram showing all the applied forces on the drop. What is the strength and direction of the electric field between the plates? What is the net electric charge on the drop? How many excess electrons are on the drop? And finally, what happens to the oil drop when the potential difference between the plates is decreased to 900 volts? Draw a free body diagram. Well, first, the drop has a mass, so it has a weight, mg, pointing down. For it not to move, which means it has an acceleration of 0, it needs a force in the upward direction, so that will be the electric force. What is the strength and direction of the electric field between the plates? Well, the charge is negative, so the electric field will point in the direction opposite to the electric force. Electric force up, electric field down. Okay, and a nice way to remember that too, if this is an electron, which it is, right, and we need a force pulling it up, what kind of charges do you need up here? You need positive charges to attract it, which means you'll have negative down here to repel it, and the electric field goes from positive to negative. That's a nice way to remember it also. Parallel plates will create a uniform electric field, which is why we have those arrows all the same size and all the same direction and spaced equal from each other. Now we use Newton's second law. We have the electric force in the up direction, so that's positive, mg in the down direction, negative, and that equals ma, but a is equal to 0. So we have Fe minus mg equals 0. Add mg to both sides, we get this. And then what is the electric force on a charge? It's just Q times E, where E is the electric field. Now, for parallel plates, one of my favorite equations, delta V is equal to ed. So in this case, we want to substitute in for E, so that would be delta V over D. That equals mg. Rearrange everything because we want to solve for Q. And we multiply both sides by D, divide by delta V. Here's our expression. So here's 99% of the problem, just getting to there. Now we substitute in the mass of the drop, the gravitational acceleration, the distance between the plates. Now we set up here it's 4 centimeters. We have to convert that to meters. Move the decimal place 2 to the left from the 4. And you get there's 1, there's 2. You get 0.04 meters. Divide by the voltage. And our charge is 1.2 times 10 to the minus 18th coulomb. How many excess electrons are there on the drop? Well, here's the total charge of the drop. Q drop is 1.92 times 10 to the minus 18th coulombs from the previous slide. The charge on an individual electron is 1.6 times 10 to the minus 19th coulombs. Now the reason we have excess electrons is because we have a net negative charge. So there are more electrons than protons, and we're going to find out how many. That number will be the total charge on the drop divided by the charge on each individual electron. We do the division, and we find that we have 12 extra electrons. What happens to the oil drop when the potential difference between the plates is decreased to 900 volts? So let's circle this here. Let's use Newton's second law. Sum of the forces is ma, electric force is up, minus the gravitational force down, and we're not going to assume that the acceleration is 0 this time. We don't know. We're going to find out. So we isolate acceleration by dividing both sides by m. And what is electric force equal to? Well, QE, so we substitute that in. What is E equal to for parallel plates? Well, delta V over D, so we substitute that in. So now let's look what we have here. Previously, the electric force and the gravitational force were the same. But now we're going to decrease the voltage, the potential here. So if you decrease that positive number and you don't change the negative number, what's going to happen? You're going to get a negative answer. Okay, just to be real quick, if you have 5 minus 5, well, that's 0. Let's decrease the first 5 to 4. 4 minus 5 is negative 1. Same thing. So the acceleration will be negative and the drop will move downwards. Or you could have just done a free body diagram and said, look, we're decreasing the voltage. That means we have a smaller electric field, so the electric force is smaller. You draw the arrow smaller, mg stays the same, and what's going to happen? Acceleration downward, just graphically as opposed to doing the algebra. Both ways work.